Okay, we're going to develop some rules for exponents. And before we do that, let's kind of review some of the rules that we have for addition and multiplication. And how do we come up with these rules? Well, if we go back to some of our basic properties of addition, like the commutative property, um, the way that we come up with this, it's kind of uh, something that you just realized. They're called axioms, and there's no real proof for them. It's just we just come to see that these are always true. And the way you do it is stepping back a level, right? So if we go back from addition to counting, right, you can see that 3 plus 2 is the same as 2 plus 3. There's still the same quantity there. And we go to associative property. We had, I don't know, 2 plus 3 plus 6. We would see that, if we added these two first, we had 3 plus 6 was 9, and then we added on 2 more, we'd get 11. Or if we did this other way, we said, let's add these two middle ones first, and we said 2 plus 3 is 5, and 5 plus 6 is also 11. So going back a level, you can kind of see the obviousness of these statements. If you had a plus nothing, right? If you just count a, we'll say it's 2 in this case, plus nothing, well, that's the same as if I just had that, right? So these are kind of like duh statements, duh, right? And then we have our definition of subtraction. If you have some number and then you take away that number, it's the same as adding its opposite. And you can make up more. There's the inverse property where a plus the opposite of a is equal to what, right? If I had any number, 2, 3, 4, 5, whatever number, and I took the opposite of that number and I added it to this, so it's like taking away 5, I end up with nothing, right? So this is 0. It's called the inverse property. And it's just a little review of addition. Multiplication works the same way. We see like, oh yeah, if we had 2 times 3, either way you multiply it. If you did 3 groups of 2 or 2 groups of 3, it's still 6 either way. And you can see that that's the case with any number that you use. If you used 4 times 3, right? So you'd have 4 groups of 3 or 3 groups of 4. Either way, it's the same number. It's 12. Okay. And then if you have some number 3, for example, and 1 time, then it's the same as the 3, right? So it's kind of another example of going down a level that these work. These always work. We also have things like multiplication over addition, and all these rules are useful when we're using them on the fly. So that's kind of why we want to build some rules for exponents as well. Multiplication over addition. This one, if you think about, okay, if I have this area model again. So let's do 3 times 4, right? Well, I could think of this as, this is 3, and this is, instead of 4, this is 1 plus 3, isn't it? 1 plus 3. So like I say, I could add those together first, and I'd say 1 plus 3 is 4, and then 4 times 3 is 12. Or I could do 3 times 1, right? 3 times 1 is 3. And then 3 times 3 is 9. And then I add them together. So I have 3 plus 9 is 12. So you can see that this is always going to be true if I use any number of cubes, like anything where I'm multiplying an area together. So if I did 4 times 2 plus 4, you would see that I could add them together first, or I could multiply each part and then add them together. It doesn't matter. That's why the distributive property works. It is the same quantity no matter what you do. So I could add them together and then multiply 4 times 6 and get 24. Or I could multiply each part. 4 times 2 is 8, and then 4 times 4 is 16, so I have 8 plus 16 is also 24, right? And then the other one was 4 times 6. It's also 24. So you would see that these numbers would always be the same, no matter what configuration you put them in. Okay, and then there are these other really duh statements like the reflexive property. A is equal to A, yeah, it's always equal to itself. Then you have things like the transitive property of A is equal to B, and so on. And B is equal to C, then A is equal to C. And then we have this nice addition property of equality. If two things are equal, then we can add something onto both sides. And we use this one a lot in algebra. Right? So if we have two things that are equal, then we can add the same thing to both sides. There's also the subtraction property of equality, multiplication, division properties of equality, where you just do the same thing to both sides. All right, so let's build some exponent rules. And we can always build onto these rules by going down a level and thinking about, well, exponents are just repeatedly multiplying. So if I have, it's useful to use a number to think about it. So if we have two things with the same base multiplied together, what is that? So let's try a number example and think about it, and it probably should be obvious once we do that. So if I have 2 to the third times 2 to the fourth, okay, so what is that? It's 2 times 2 times 2, and then it's times 2 times 2 times 2 times 2, right? Repeatedly multiplying it times itself 4 times and 3 times. So what is another way that I could write this? Well, it's just the same thing multiplied times itself 7 times now, right? Just count them up. So it's 2 to the 7th. So is there a way I could jump straight from this to this? You know, like when I get bigger numbers, it's going to be really tiring for me to write all out. So what if it was 2 to the 34th times 2 to the 127th? Okay, would I want to write out all of those 2's? It would take me a really long time, right? So I would write down 34 of them, and then I would write down another 127 of them, and then I would count them up, right? So what really happens here is all I do is I could add, it's going to be 34, I just count them, right? And then count on, so I count on another 127. So that's just repeatedly counting on is adding, right? So this would be 2 to the 34 plus 127 power, right? So that's a rule that we can make for this exponent. We say, well, it's going to be the same base, x, and then it's going to be a plus b. Okay. That's another thing that we could do. How about, what if it was x to the a divided by x to the b? Well, let's just try our number example here. How about 3 to the 5th divided by 3 cubed? Okay, so this would be the same as 3 times 3 times 3 times 3 times 3 divided by 3 times 3 times 3. Right, and if I do 3 divided by 3, what do you get? And that's another thing that we could have wrote in our multiplication rules. We could have said, well, what is any number divided by itself? Well, when you take 3 and then you divide it into 3 parts, you find out that you get 1, right? And if you take 5 and divide it into 5 parts, you get 1. So that is called the inverse. That's the inverse for multiplication. And it's the inverse and identity property are kind of linked together, and we'll get into that more in algebra. But you see that if you do the inverse, you can get 0 in addition and a 1 in multiplication. But back to this. So we say 3 divided by 3 is going to be a 1. So 1 and a 1, and this is a 1 and a 1 and a 1 and a 1. So what is 3 times 3 times 1 times 1 times 1? Well, multiplying by 1 doesn't change the value, right? Remember that thing? Anything times 1 is itself. So 3 times 1 is 3, and so all these are 3's, and then 3 times 3 is just 3 squared, isn't it? And then all these divided by 1 doesn't change the value, right? So dividing by 1 is the same as multiplying by 1. Doesn't change the value, so we can just ignore them. So this would just be the same as 3 times 3, which written as an exponent would be 3 times itself 2 times, so it would be 3 squared. Okay, so that's one way you can do it, is just turn it into a repeatedly multiplying problem. Or you can think about what would it be if I had a really big number, right? 3 to the 147th over 3 to the 34th, right? I would not want to write out all those 3's. And I would not want to write out all those 3's. But you can think that every single one that's on the bottom and also on the top is going to be a 1. So they will cancel each other out, or turn them into 1's. So it's basically going to be 147, and I'm going to take away 34 of the ones on top, so it's going to be minus 34. So you can make this rule that x to the a over x to the b is the same as x to the a minus b. Okay, so that's the rules that we'll use for now.